Joint aided inference of Gaussian process-driven differential equations. This work was done with a kind of big team of people across the University of Makerere in Uganda, Sheffield and Nottingham, and also in collaboration with AirQO, who are a team of people working in Uganda to monitor air quality. So kind of the general outline of my talk, I'm going to first start talking about air pollution in Kampala and modeling air pollution in general and how we might do that with maths. I'll then talk a little bit about inference for linear systems. So if we've got some kind of variable of interest u with a linear system applied to it, driven by some forcing function f, can we learn things about the forcing function and can we learn things about the linear system? Given noisy measurements of u, can we infer f? I'll talk a little bit about adjoints, which are operators which have this property under kind of RKS spaces, and then I'll give a couple of examples of how I work, what we've done with the work. So 7 million people die every year from exposure to air pollution, the majority of those in low to middle income countries. The UK government estimates that the annual mortality from human-made air pollution to be nearly, 28,000 to 36,000 deaths and cost the UK a huge amount of money. And these are this encompasses kind of all pollutants, so we're looking at particulate matter, but also carbon dioxide and other nasty things one might breathe in. So the kind of focus, the reason this work came together is this company AirQO in Kampala, who are creating kind of portable air filters, air quality monitors to measure particulate matter, and some of them go on these motorbike taxis. So we have like moving observations, and then some are static. And then the reason that we've kind of put these in is that it's really expensive to accurately measure air pollution. You can imagine if you've got a sensor that's trying to work out how much particulate matter is in a place, that thing's filling with particulate matter, which makes them difficult, and it makes these kind of smaller sensors, cheaper sensors really nice to use, but also they're more prone to breakages, and there's some calibration problems and things that go with that. I won't talk about that very much today. So AirQO have developed these cheap sensors that cost way less money, and then deployed them around Kampala, and they're measuring PM2.5 and PM10, so that's particulate matter 2.5 microns or less across, or 10 microns or less across. So a little snapshot of the PM2.5 in Kampala from 2023. You really cannot see those numbers, but I can tell you that the highest ones are about 75. The World Health Organization guidelines are 5 micrograms per meters cubed. London in 2022 had an average of 9.6 micrograms per meters cubed, and the 20-year average for the UK is 11. The UK government's aim for London is 10, so still double the WHO guideline. And actually in 2023, London hit about 8 micrograms per meters cubed, but apparently that's largely because it was raining a lot. So the PM2.5 was getting kind of absorbed and taken to the ground. So what we decided to try and build to look at this was an air pollution digital twin. So we wanted to model the air pollution U of X and T, so that's our concentration, over like an entire area or a city. And the two things we want to do are infer the air pollution. So like if we know how polluted one area is, can we predict it for another? But we also want to be able to infer the pollution sources. So standard non-parametric models, e.g. Gaussian processes, aren't able to do that. They can do the first point. If you can interpolate from kind of one area to another, but we can't infer the pollution sources because we haven't got that kind of inverse power with the Gaussian process. So instead, we wanted to build models that both know data and also we enforce some physics into. So this is the advection diffusion reaction equation, and anyone who's done any kind of applied maths will almost certainly have seen it. To go through the terms, du by dt, that's the way the concentration changes over time. That next term is the advection term, so that's how concentration changes due to wind or kind of fluid movement. The next term is then how the concentration changes to dispersion. And the last term is a reaction term, so that's if our kind of pollutant is being absorbed in places or absorbed in general. And then the final term, the sum of f's, so those are our different pollution sources across a city or across a kind of area. And this is a pretty general model. You can use it by changing the parameters. You can use it to model whatever kind of pollutants you might like. And what we hope is that by including these kind of mechanistic behaviors and encoding the physics into this kind of data-driven model, we're better able to kind of plan interventions, predict behavior, but also, like I say, comes back to this being able to infer the pollution sources because we know something about how things are moving. I'm sorry, I can't remember what that line says. Oh, okay, we can also extend the model with a GP to capture some of the missing physics because, you know, we can't capture everything in this single line necessarily. So then our computational challenge, the thing we're trying to do, if we have some noisy measurements, which we know are noisy because our sensors aren't very good, if we have some noisy measurements of pollution levels, are we then able to infer the concentration field over the space, the unknown source terms, and, if possible, the diffusion, advection, and reaction parameters, and then any kind of hyperparameters that we might build into a statistical model. And the way that we want to try and do this, and how it is that I'm here talking to you, is that we choose to use Gaussian process priors over our forcing functions, where we can kind of carefully choose potentially prior, mean, and covariance functions to account for kind of places that a priori we think might be causing more pollution. So kind of industrial regions, you can build things like roads and power stations into the shape of your GP priors, and then potentially things like varying socioeconomic factors across the regions, because that will have a big effect. Things that happen in Kampala is that in certain areas people burn a lot of their waste rather than it going to landfill, and that's going to have a big effect on particulate matter. So a kind of little overview of linear systems. So we have some kind of linear system with an unknown parameter here. Kind of LP is denoting our linear system. U, again, our kind of concentration or our variable of interest, and F, our forcing function. Finding, if we know P and F, we kind of run this forward, and that's our forward problem. But what we've got here is the inverse to that problem. So we want to infer U, F, and P given some noisy observations of U. And again, here are observations given by Z. H is some kind of observation function, so if that's kind of averaging over a small time, or a delta function if we know it's doing very like exact measurements, plus some normal error. You might think, hey, why don't you just use MCMC for something like this? And the answer is that it's really, really expensive to do. It requires one solution to the forward model for every iteration of the MCMC. So if you're running like 40,000 iterations of MCMC, it takes a lot of time and goes very slowly. And we'd like to do something cleverer than that, I think. So then there's kind of two potential approaches to how we might find these unknown parameters. So the first is a kind of frequentist approach. You do some maximum likelihood estimation, and you find the P and F that minimize your some cost function. And then the other is the kind of Bayesian approach, where you want to find a posterior distribution given your data. So then we've got this framework. We've got our air pollution digital twin, and we have a problem, which is we want to infer the sources. But what are the things we need to do to achieve that? So we want a method to perform efficient inference, so something faster than MCMC ideally. And we also want a way to model F that fits into that inference framework. So that efficient inference brings me to the adjoint operator. So if our linear operator L between U and V, where U and V are Hilbert spaces, then the adjoint to L is L star, which satisfies this kind of series of inner product operations. And I'm pretty sure the way it works is that for any linear operator, there is an adjoint operator in that Hilbert space. And this is known as the bilinear identity. But this it does extend for the kind of analysts amongst us. This does extend to any Banach space, but we're happy with Hilbert spaces for today. So adjoints have some kind of useful properties for us. They allow us to calculate the derivative of some cost function as a kind of side effect of the way they're generated. And they can be used to easily compute our least squares estimate. So it's a little example of what an adjoint operator is. So if our linear operator is just matrix multiplication, then our adjoint operator is the transpose of that matrix. And you can do the little bit of maths to prove that in your own time. So then how do we, so we've got these adjoint operators, how do we use those for efficient inference? So we've got our linear system, and we've got our observations with this observation function h. And when we're also assuming the observation function is linear itself, so you can represent it with an inner product. And we want to consider the n adjoint systems. So this is our adjoint operator applied to our observations. This is our adjoint operator applied to our kind of our v from the previous slide. I'm going the wrong way. Applied to our v from the previous slide. Which way am I going? Sorry. Adjoint operator to v from our previous slide equal to our observation. And then using the linearity of the observation and the adjoint, we can show that our observation operator over U is equal to the inner product of V, which is the solution to this adjoint system, inner producted with F. Sorry, I realize this is like really maths dense. It will make more sense, I promise. So then we know that our observation, HI of U plus some error, is also equal to this inner product between the solution to the adjoint and our forcing function plus some error. And if we suppose then that F is some parametric model with a linear dependence on unknown parameters, we can use the linearity of inner products to write our observation instead as this linear sum, which means that we've got a linear model. And the way that we treat learning in linear models is well established, which is good for us. We like that. So then we can write the complete observation vector as this gram matrix, as we covered earlier, multiplied by our weights plus an error. And we know that, kind of from standard results, that minimizing our frequentist problem has this given outcome. And this solution, and then so you have the kind of solution, you have, this is like, sorry, yeah, so then Q hat minimizes this, and that's a kind of known outcome. And we have the same in the Bayesian setting, whereas if we put a normal prior over our Q, which are these unknown weights on our sum, then the posterior is given by this normal distribution with mu n and sigma n, and mu n and sigma n are given by that. I'm not going to run through the algebra for that today. I hope that's okay with everyone, and you're willing to trust me. We can talk about it more if you'd like to. So this is so that's kind of so that sets up our efficient inference. We now know that given observations, we have an exact form for our posterior. We've written it down. So then the next step is, now that we've got our efficient inference, how do we express f in such a way that we can fit it into this setup? So this is your third intro for the day to Gaussian processes. I will keep it really quick on that basis. And I think, and we've also got some more versions of our favorite plots. Doing well on this. But yeah, so Gaussian process, essentially a distribution over functions, which, as we've all just learned in the lab, you can condition to data points to fit your data. And Rich has already covered this to some degree about why one might use GPs, but there's a lot of kind of mathematically attractive reasons that you might. They're closed under addition, so a Gaussian process added to a Gaussian process is also a Gaussian process. They're closed under Bayesian conditioning. So if we observe some number of points, then f given those observed points is also a Gaussian process, but with these kind of updated mean and covariance functions, your posterior mean and covariance. And it's also closed under any linear operator. So if we apply a linear operator to a GP, that's also still a GP, which means that you can differentiate, integrate, multiply by a matrix. And also they're the best linear unbiased predictors, so they're kind of, they're natural statistically, as it were. So then we've said that we would like our forcing function to be a GP, but then we've also said we'd like our forcing function to be a linear sum. And how do we kind of get those two things to come together? And the answer is that we can, if we let f be a reproducing kernel Hilbert space associated with some kernel k, and we have an orthonormal basis for k, for f, we can express our Gaussian process as a linear sum. And if we truncate that linear sum, we've got a finite linear sum, which means that we can plug it directly into our inference methods. And in this, we approximate a GP with a linear model. Obviously, as you increase the number of bases, the closer you get to you kind of reproducing your original GP. There's lots of possible bases that will kind of fulfill our needs here, and you can generate a GP with. So there's the Mercer basis, which take this integral over the kernel, and the Carhonen-Lerver theorem says that this choice is mean square optimal. There's random Fourier features, which you can use as a basis, and Bochner's theorem tells us that this integral is equal to the kernel. And using that, we can let our bases be these kind of cosine bases, which is what we used for this project. And you have these random weights Wi and Bi to do that. If you're interested in non-Euclidean domains, you can also use the Laplacian basis. We're not interested in non-Euclidean domains in this context, but I just wanted to show you that we could do that if we wanted to. So there, we've now got our means of efficient inference, and we've also got a way of representing our forcing function as a GP, but within that linear system. So for our algorithm, for a given linear system with an unknown forcing function f and some noisy observation z, we can first choose a basis expression for f, so we express f, this Gaussian process, as a linear system. We can determine our adjoint operator. So for things like PDEs, the adjoint operator is well known. If you read S-step from 2004, there's just a given way of getting your adjoint back. Or you can solve the bilinear identity and work it out for yourself. Then we solve that adjoint system n times, where n is our number of observations. We compute our big regressor matrix phi, where that phi is this inner product of the solutions to that and our basis vectors. And then with all that, we have an exact solution for our posterior distribution for the weights of Q, which are these weights that determine what F is. And if we've got a posterior for Q, then we have a posterior for F. And then you can run your forward function with that posterior for F in it to get a posterior for U, which was our concentration. So first example is partial differential equation. So as I said before, this is the advection diffusion reaction, advection diffusion reaction equation, which is linear operator. And so we want to solve this equal to some forcing function. And then our inverse problem, we assume that f is a Gaussian process, and we want to estimate f given noisy parameters. Hi here are kind of our sensor functions, so this is how we are recording our amount of pollution, and we've essentially decided that these just average over a chunk of space and time. And if you want to make, if you want it to be like a kind of pinpoint, you can make that averaging very, very small. Or some sensors take really long readings, so you can extend the size of that averaging, and the method's pretty much fine with either. The adjoint system is derived by integrating by parts twice, and that's what the adjoint looks like. You'll notice it looks very, very similar to the advection diffusion reaction equation, just with a couple of swapping of signs. Like I say, you can either integrate by parts twice, which is like a bit about a page of algebra. Again, happy to talk you through it if you'd like, but I don't think I'm going to cover it here. And then if we have n observations, we need n adjoint equations. So this is L star applied to VI equal to our observation function. So essentially, you're running this differential equation to solve for VI. And you know what HI because those are your observation functions. You've set those as the user. If we use the initial boundary conditions of u of x and 0 equals 0 for all x in the domain, and the outward gradient on u equal to 0 for all x on the gradient, then we can generate the final and boundary conditions for the adjoint system so that it's well posed, and we can show that those are vi of x and at the final time is equal to 0 for all x in the domain, and then you have this kind of what's called a Robin boundary condition, so you've got a combination of the differentiated vi and vi itself equal to 0, and those are then dependent on P1 and P2, which are our parameters from the linear system. And so then what this then comes up against is, though we've got an exact solution for our posterior, you might still find you have numerical issues. you're running a system of PDEs, and that's always got potential problems depending on how you discretize and your choices for kind of whether you're using things like finite elements or finite differences. Things like anyone who's used the advection diffusion reaction equations before will know that kind of the ratio between your advection and your diffusion can be really, really problematic. Things break really, really fast if you've got a nasty Reynolds number, not Reynolds number, if you've got the nasty ratio of those two. But those are things that you'd be fighting up against whatever way if you're doing these kind of physics-informed models. Also, the cost of solving the adjoint is the same as the cost of solving the forward problem. They have the same form. They're kind of similarly difficult. So then I've got some results here. This is the posterior mean so we ran the forward model in 3 dimensions. That's 2 spatial dimensions and 1 time forward, and then looked at kind of just 1 slice to see how we were doing. So then this is the ground truth of U, so that's our pollution at that time. And then this is our inference of it with 4 sensors. And you can see we don't do particularly well, but we kind of pick up some areas. And then at 16 sensors, we're doing like a pretty good job of recreating that pollution field. And we can also show the variance over those. And this is also where the sensor locations are. And you can see that the variance is lower around the sensors. You can also see that, so in this case, the wind, the advection, is traveling just in like a kind of straight line along x equals y. And you can kind of see on those variances that we have less variance as we kind of travel up towards the sensor, which we'd expect because the system knows that any pollution from kind of down here is getting brought up here, but we know less after the sensor because we don't really know what the wind, where the wind is taking it in that way. And you can also see that in the 16 sensor case, we're at kind of very low variance across, apart from that kind of top corner where we're kind of blowing away from the sensors. So then we had a little look at the effect of length scale on our sources and found that the system's very, very good if your length scale is long. So if you've got a very smooth kind of distribution of pollution, then we do a pretty good job of predicting it. But then as the length scale increases, our prediction gets worse. So essentially things dot around more and more. I say it gets worse, we still do a relatively good job. But it becomes harder and harder to kind of account for those big changes in the source. Hello. Yeah, this is synthetic data, yeah.
And could you not estimate it?
Or estimate the length scale? Or, yeah. So we could, in this case, because we've set we know what the true is, we can just directly replicate the true, if that makes sense. We know that,
So those are with the actual...
Yes, yeah, those are the true ones. Yes, yeah. Yeah, sorry. This was just to indicate that the problem, we don't necessarily get worse, but the problem itself gets harder when you've got shorter length scales for the... Yes. So I think it's still 25.
Right, so ideally, the length scale change, you should be small.
Yes, yeah, exactly. Yeah, that's exactly the right thing. So you can, if you want to, try and infer those kind of Q weights using MCMC, but it's really, really expensive. So so this is if we express our Gaussian process with just 10 weights, 10 basis vectors. You can generate these Q values, and these match up exactly with the ones that come out of the Gaussian process approach. But we need thousands of ODE solves to generate these values versus just 10 ODE solves using the adjoint method. And the MCMC takes longer and longer to converge the more features you have. When I ran it I think I ran it for 50 features, and we were looking at, I think, no convergence after something like 50,000 iterations. So then just a little look at the results. So this is the median MSE as a function of the number of sensors and basis vectors. So this is like a pretty horrible table to look at, and I apologize. But essentially, we do better as we get more sensors and as we approximate our GP with more basis vectors. So when we were running this, when we were generating our toy data, our true GP had something like 500, maybe like 1,000 basis vectors, so very, very close to kind of the actual GP. And then when we were trying to infer it, we inferred it with the GPs of kind of increasing number of basis vectors. And as you get closer and closer to kind of well, as you get closer and closer to the number of basis vectors used to generate the toy data, then you get better and better inference, essentially. But then obviously that increases the cost. So then we wanted to, so that's all just on toy data. We wanted to test this on real data and see how well we could do. So we tested against the Roundhill 2 experiment, which was done in 1957. And essentially someone left a single source of pollutant just in the middle of the field and kind of let it blow out across. And then there were concentric rings of sensors that all recorded for like different lengths of time, which is where we used our kind of our variable time observation functions. As a constant source of sulfur dioxide released over a 10-minute period. So then, as I said earlier, we can't compare. So a GP can kind of look at the field of pollution, but it can't infer the sources. But we did want to compare just like the GP inferred concentration against the adjoint inferred concentration. And you can see that here we just tested on the middle row of sensors. And you can see that the kind of GP method infers kind of much larger predictions on the kind of right side of that sensor array, whereas the adjoint method with the kind of physics baked into it does a kind of better job of inferring the true values. And then kind of looking at source inference. So the circle there is the true location of the source, and our model in this case infers it kind of slightly upwind of the true location. And also with this kind of slight negative dip in source, which we think is essentially that we've got some of the parameters wrong. So it's kind of overestimating the source in one place, correcting that by underestimating it somewhere else, and we end up with a kind of, but we still end up with this quite good result for the concentration. And this is the kind of problem, is that you can't ever score against your source. You can only score against the observed data, which is the concentration, unless you somehow know your pollution source very, very well. And then we also kind of looked at whether we could, if we, as I said before, with the toy data, we were running the kind of true GP. We just ran the same variables for the length, we ran the same values for the length scale. But then we said, okay, if we thought we didn't know the true values, can we infer them? So we kind of did a very naive Bayesian optimization and found that to some degree, up to kind of some degree, we can find those values. But this does bring us onto kind of quite a big problem, and a problem that we think is maybe kind of endemic across all of this kind of like latent force working out, in that if you don't know the parameters of your linear model, and you also don't know your forcing function, then you have a kind of key identifiability problem. So I've got here is two different sources that I think this is just Gaussian distribution, it's a Gaussian blob, and this one is kind of a kind of stretched line of positive source next to a stretched line of negative source. And if you run the forward model with two different parameter sets, you can get exactly the same observed concentration. And this poses a problem for us, right? In the real world, where we don't necessarily know like how fast things are diffusing, we don't know how fast things are reacting. So it's easy to get things wrong, which I think, again, is why we ended up with this problem here, where we've got the negative and positive source. In that it means that if you leave everything unconstrained, you can nearly always get, again, because you can only score on the observed concentration, you can end up with a perfect score comparing your inferred concentration to the true concentration, but have got the forcing function totally wrong. And we think this is probably a problem for other people, and if it's a problem for you, I'd be really interested to talk about it, because we have been thinking about ways to solve it. And the ways that we've been thinking about are, one is that we hope we know more about the problem. So can we constrain our prior distribution over the advection, over the wind, by some kind of measurement? This is the kind of general approach that people in engineering have previously taken. They just said we know the parameters better than knowing nothing about them. You can assume some of your parameters are completely known. So again, if you're working in like kind of a well-observed field, you can say, yeah, we know that PM2.5 always dissipates at this kind of rate on water, for example, if you wanted to look at your reaction term. And then the other thing that we don't think people have done very much before is trying to constrain your source distribution. So are there things that we can know about our forcing function f? For example, you might believe that it's never negative, there's never a sink. And there are ways that we've looked at of constraining that. So you set it always greater than 0, for example. That does slightly mess with how Gaussian a Gaussian process it is in some cases. But this is one of those things where it's coming down to like how interested are we in what the user wants at the end versus how kind of mathematically pure our work remains. But that, which is a conversation in its own right, I think. Yes, yeah. Sorry, say that again. Yes, yeah. Yeah, absolutely, yeah. But again, but then that does, the problem with all of these options, all of these methods really is that it relies on you thinking you know something about the source. But yes, absolutely, you could do something along those lines. This is just like a little aside, or not aside, but an additional thing, is that because of the kind of linear nature of our model, it's actually really easy to add new data. You just kind of incorporate it into the big gram matrix. It simply just adds new rows to the big phi matrix, which is quite nice if, for example, you in kind of your process learn some new information, you can like add to your prior. So in terms of the costs of using this system, so the adjoint method requires n, where n is your number of observations, solves of your adjoint system to infer f. It's essentially insensitive to the number of basis functions used, kind of like technically, mathematically, less true computationally sometimes. And the kind of non-linear parameters, like GP hyperparameters or PDE parameters, can be inferred in an outer loop if you want to, but as I've shown, there are some problems there in terms of that identifiability. From what we've looked at, the kind of GP hyperparameters seem to be a little bit more identifiable. If you get your length scale totally wrong, you'll really know in your predictions. But there's still kind of up for debate over how useful that can be. And then comparing that to MCMC, you can infer all of your parameters together, so that's both your Qs and your hyperparameters. But it's really hard to say how many iterations are required, and it grows a lot with the number of parameters probably. And as we said before, it's very expensive. The number of iterations is very dependent on your number of observations. And as with MCMC, if you can get access to derivative information, it can speed things up a little. So to conclude, a lot earlier, I must have talked very fast, sorry. But to conclude, we have developed a method to infer forcing functions of linear systems giving noisy observations, which we can't do with standard methods. We require kind of the number of observations worth of adjoint solves to infer the posterior, and we're essentially insensitive to the number of basis functions we use. The adjoint gives us some numerical stability, gives us numerical stable derivatives of the cost function with respect to other parameters, and kind of cost functions if we want it. I didn't talk about that very much here. And there kind of are opportunities here to kind of increase the efficiency. We've looked at a little bit of efficient use of adjoint simulations. If we know how things, if we have kind of identical sensor functions, you can kind of move the adjoint simulations around the domain and they'll look identically the same because of the way that the advection diffusion equation works. There's opportunities for a gradient-based optimization because we can pull gradients out of the adjoint. And like I mentioned earlier, you can add this sequential data. If you'd like to read more about this, we had a paper at NeurIPS in 2022. And then there's a new paper, hopefully forthcoming to preprints end of this year, where we talk a lot more about the kind of identifiability problems and the solutions we've tried to take to solve those. And yeah, thank you so much for listening. Has anyone got any questions? Hello. So we don't really have a kernel matrix because of this linear description. Where's that gone? So yeah, because of this, so we essentially express our GP entirely via this linear sum. So yes, yeah. And essentially this, so this kind of bottom two lines, the weights, the WI and BI determine the kind of hyperparameters of your, this is for an RBF kernel, but you can essentially determine those hyperparameters with the weights.
Was that choice driven by computation, or was it fit well?
So yeah, in this case, it was it fits well. It's nice to use cosines. We looked at using other bases. We looked at just using kind of Gaussian blobs, but what you find is that you need loads more of them because obviously a cosine covers the whole domain, whereas a kind of Gaussian blob obviously has kind of near zero tails. So you need loads and loads and loads of them to cover. That was actually one of the things we were thinking about when we were trying to do more kind of constraining to positive. So we were hoping we could constrain, if we could constrain the weights positive and only have Gaussian blobs as our bases, then we constrain the whole thing to positive. It turned out to be not very happy with that. I'm computationally unhappy.
Just more in general, regardless of which basis you chose, was the choice to do this instead of a traditional GPMI
Oh, so the thing with the reason, so you mean having the linear system equal just to a traditional GP rather than constraining it, or do you mean just why use the linear system? Sorry, yeah, no, that's probably, no, that's almost certainly my fault. No, so what it is that with the differential equation, we're having it equal to some unknown forcing function. And we want to know what that forcing function is, but we have no real-world data about that. We don't know what it looks like at all. All we know is that it's driving the outputs of this physics-based model. And so a traditional GP has nothing to condition on to find that out. Whereas if you build the GP into this physics-based model, then you're kind of teaching the GP some physics, which is why if you were only interested in knowing the kind of pollution over the space, then a GP is fine. We think doing this might be more accurate because, again, we've constrained some of the physical knowledge. But you absolutely could just use a GP if you wanted to, if that was your only interest. If you're not interested in the forcing function, traditional GP is fine.
But when you're using it to model this forcing function, does it then become more natural to do this?
Yes, yeah. Oh, so this all kind of comes in with the, because we want it to, we want these like nice known solutions. So you want your forcing function to be a linear sum so that you can get this Q hat or kind of posterior for Q analytically. And we already know from previous work that you can write a GP this way, which is why you use the basis functions. Cool. That makes sense. Cool. Hi. Yes. So what you say, when you say a number of inputs that lead to the same output, in terms of the identifiability, we haven't really thought about it. So one of the kind of naive solutions that we were thinking about is that you just run it loads of times with loads of different sets of PDE parameters and then do a model selection. But again, I think all of the kind of solutions to the identifiability problem annoyingly come down to a priori knowledge. Yeah, does that answer the question? Vaguely? No? Sorry. Maybe we can talk about it after. And yeah. Okay. I think there was maybe a question in the back.
Yeah, with some of these other like latent force models, you kind of boil down to it's the thing you said at the start when you showed it like really weird looking curve, and
Yeah.
kind of takes into account the situation you're in. Is it possible to calculate one of those for this?
We haven't tried to, but potentially. Yeah. I don't know. Rich, do you have any intuition on that?
I mean, Rich says for the stats.
Sorry, Maurizio, do you have any interest?
Read function, right, to do that, and yes, you probably went over each page. I think we're going to do the calculation, but it went many pages. As soon as you change the model slightly, you have to do it again. So if you have a Green's function, our conclusion was that's a better approach. That Green's function is essentially a solution, right, not an analytical solution. If you depend upon numerical solvers, this is what we're saying is an attractive alternative. Is that fair, Maurizio?
We need a postdoc to work. I think we spent a lot of time on this solution, and I think we haven't spent equal amount of time in the other approach. But we did derive the equations for the kernel. But yeah, when we tried to do some comparisons, I think it didn't scale as easy as with the numerical approach, because you wouldn't then need to go to sparse methods to inducing points to do something like that. But yeah, I think this is still an area to explore there.
Yeah, definitely. Sorry, thank you. Yes, hi.
I guess it would be quite easy for you to incorporate some additional covariance into your model. For example, if you talk about these kind of air pollution, like wind speed, that's quite helpful when you do get these new from visual.
Yeah, absolutely.
So that's the, let's say, assume without the wind speed, you just feed it into the model.
Yes.
Would that make it much faster in terms of covariance?
Yeah, quite possibly. I mean, so with the example I gave of the round hill, they had recorded the wind speed, so we just plugged it straight in. But then again, yes, we do. I think that might be the, well, so one of the potential problems sorry, it's so far back. So there's a few things that are potential problems for the round hill, right? I mean, to some degree, round hill's a bad example for us, because we have said we think our forcing function is like a Gaussian process, but this is a point source, like this is a delta function, which is like not very well represented by a smooth kernel over the thing. So to some degree, we were just kind of happy we got close. But there's other problems, right? One is that round hill's in 3D, and we're only modeling this in 2D. It's one of the things that it's going to extend to in the next paper, is we've extended this into 3D, which is it's pretty trivial, really. You just add another layer to everything of the forward and backward model. The other thing is that the diffusion, or the wind speed, is relatively well known, but the diffusion's not. So getting the diffusion wrong here is quite possibly the reason we've got this kind of positive, negative skew. And we haven't, so in all of these cases, we haven't tried to learn any of those parameters, because what I found on a much simpler example is if you try and learn everything simultaneously, it sends all the parameters to 0 and makes the forcing function look like the concentration. So essentially, yeah. Yes, you'd have to be like I think you mentioned earlier, maybe penalizing against something. You have to be penalizing against something else to stop that from happening, essentially. Cool. No problem. Hi.
Sorry, just a couple of questions.
Sure.
The first one was about the iterating with PDE. So it wasn't clear to me why you're doing that.
Why we're solving. When you say iterating PDEs, do you mean the kind of L star VI equals HI solves? Yeah, cool. Sorry, I really did go through this too fast. I apologize. So this is because of where's the nice bit of maths? Yes, so this is because of this nice bit of maths. Because we know that the observation is equal to the inner product of the solution to that adjoint and the forcing function, we need to get the solution to that adjoint. So we run L star VI equals HI, which essentially is just running the PDE, get VI out, and then take the inner product of VI and F to give our observation back, essentially.
How are you doing that? Are you using like Euler integration?
So this was just I think this was just finite differences for this problem. For kind of more complicated problems, and when things get a bit messier, we've also been having a look at Lagrangian, so non-mesh-based kind of PDE solvers.
My other one was, if you wanted to adapt this like non-linear settings, like do you incorporate the Jacobian into the denominator of the posterior calculation?
I don't know. So we haven't, because this all hinges on the bilinear identity. We haven't really looked at extending it to nonlinear at all. Because essentially, like, we thought about it, and then you get one line into the algebra, and it's like, oh, it just doesn't work. The only, if you want to run this particular inference method, you have to linearize your nonlinear thing, I think.
I mean, that assumption baked in at the start because you assume it's a map space? Or
Yeah.
So, already from that assumption, you can't. You're saying from that assumption, you cannot?
It's just that we need, I don't know if it's the Banach space necessarily that's the problem. I think it's well, so one of the problems is the existence of the adjoint. And you're guaranteed those for linear things, and you're not guaranteed them for nonlinear things. And the other is that there is one of the particular lines of the kind of like analysis to get there requires it to get that linear model to give you your nice exact solutions, essentially. If you want to talk about it further, I will think about it harder and work out which bit it is specifically that breaks it, because it's been a while since I tried to break it. I think that's no more hands up, I think, maybe. Cool. Yeah, thank you all so much.